So to construct an algorithm out of this idea, I need more notation. I need to be able to express this stuff completely. So first, let's just make sure that we understand how we're writing down all of these distances between the nodes. So I'm going to write the distance between node I and j as d sub ij. Okay, so the distance from I to j is going to be written as d sub ij. Okay, and notice that in the most general formulations of this problem, dij might actually not be equal to dji. So just keep that in mind, right? It's not going to come into play right here in this very instant, but there's no reason why the distance from me to you has to be the same as the distance from you to me. And you might say, well, hang on a sec, right? If I draw a line on a map, like it doesn't matter whether I write my ruler this way or this way. But you know, the reality is, like, the answer to that is that cost need not be just distance, right? The distance from here to the top of Pikes Peak is the same as like the straight line distance from the top of Pikes Peak to here. But you're going to feel different if you walk from here to the top of Pikes Peak versus walking from the top of Pikes Peak to here, right? Those are they have two different costs. And I know this from my personal experience with Pikes Peak Marathon stuff over the summer, right? There's a difference between going up and going down. So the distance could be different in different directions, just as a note. Anyway, the distance from I to j is going to be written dij. And I'm going to write the following function to capture the costs, kind of the optimal costs of these kinds of subproblems. So what I'm going to do is I'm going to write C of, and then just in the context of our example, I'll just write it like this: C of B, C, and D, comma A, as the cost of an optimal path starting at A and going to A. Right? So this is going to be the cost. In fact, this is defined as the cost of an optimal path from A to A, right? Where that second A is what matters, right? This first A in the definition is just baked into the definition. We're just going to assume that all of our paths begin at a particular node. And then the second A is going to be kind of where the path stops. So it'll be the last node in the path. And then passing through, or I should say containing every node B, C, D exactly once. One time. So just to make things ultra clear, I'm going to draw these in color, and you know, the things in my definition, I'll connect them explicitly to the statement of the cost. And so, you know, what I can write is that the cost of the optimal path from A to A, passing through B, C, and D, hopefully can be written in terms of optimal costs of subpaths. Okay, so let's think about what the DP step is going to look like in this algorithm. And it's going to look something like this. So we're going to say, look, the cost of the path from A to A passing through B, C, and D, so B, C, and D, all the way to A, has to be one of three things. So why does it have to be one of three things, right? What are these three things? Well, the three things are these nodes. So remember, what we're doing with our DP idea here is we're taking an optimal path and we're removing the last segment and then saying what's left has to be optimal. So if you remove the last segment, let's think about what nodes could possibly be the penultimate node, right? The second to last node. Well, I mean, if we don't know anything about the problem, those nodes could be any of B, C, or D, right? Those are the three possibilities. So let's ask, in fact, we've already done the math already to see what happens if C is the last node. So for our first one, let's ask what if C is the last node? And so this is always going to be a minimum of three things. Those three things are going to be what if B is the last node, the second to last node? What if C is the second to last node? And what if D is the second to last node? So we've already done the math for what if C is the second to last node. So let's just plug that in here and then proceed. So it could be if C is the second to last node. Now what does that look like? Well, then the cost of the path from A to A has to be equal to the cost of the path from A to C plus the distance from C to A. Right? So there's our DP step, right? There's our little recursive call to C. So what we'll say is this has to be equal to, this is if, right? There's always an if in DPs. If C is the second to last node, then the optimal path has to be equal to the cost of a path passing through B and D, ending on C, plus the distance from C to A. Okay? This is it. This is exactly what we just did above. We said, look, here's our path. Here's our path from A to A. And we observed it ends, it's the second to last node is C. So then we said, well, that path has to contain the optimal path from A to C down there. And the cost of this one is the cost of this one plus 2. Done. Right? The math is there. The math is in front of you, right? So the cost of a path from A to A has to be the cost of the path from A to the second to last node plus the distance from the second to last node to A. And that's what we're capturing right here in our DP math. And we can just generalize this to the other nodes as well, right? So this is what, that middle one there is what happens if C is the penultimate node, but it could be that B is the penultimate node, in which case we have the cost of the overall minimum cost path is equal to the cost of the path passing through C and D, ending on B, plus the distance from B to A. Right, the distance from B back to the start. Or it could be the cost of a minimum cost path passing through, now what are we left with? D, so passing through B and C exactly once each, ending on D, and then going directly from D to A. So the distance then from D to A. Okay, and that's it. Those are the three possibilities. So when I have n nodes, kind of this last DP step is going to compare n minus 1 possibilities, right? So here I've got 4 nodes. I've got A, B, C, and D. I know that my optimal tour has to end at A, and so the penultimate node, the second to last node, has to be either B, C, or D. And if it's B, then what I know about that subpath is it includes C and D in it somewhere, and then it ends on B, and then the remaining distance to get me back to A is the distance just of the link from B to A. And the same logic follows through for the other two. Okay, so this is kind of the core DP idea that lets us build an algorithm. So what remains now is to generalize this. So let's generalize this beyond simply the 4-node example. We'll generalize it to a more than 4-node example, an n-node example, and then once we have that, we can analyze it for its time complexity. So in the next video, we'll start by generalizing, and then we'll think about time complexity.